Good morning, good morning. We are back in the grand scheme of actually putting together the code to start training. That'll be the next few videos on just setting up whatever actual programmatic language is needed to set up the things necessary to start training. Let's actually start training the data. I understand that we don't have necessarily enough data to train. I understand we don't have enough yet to properly have it learn, but we'll think of this as kind of just the first step into that right direction. And then from there, we could add more data. So, let's start with the first question of what is missing, right? It's actually day 15. It's gonna be training one. So what missing pieces? What are our missing pieces, right? Now we kind of have an understanding now that we need nodes, we need activation functions, we need weights, biases, outputs, right? So the real first question is how do we begin to code the training? A model that learns from labeled data. We're going for the supervised. Supervised means we are giving it the labeled data. We are saying this is a cornerback. We are saying this is a receiver. Um, so from here, we are saying that we are building a model that learns from labeled data. What are your inputs X and labels Y? So input X is going to be your image, and then the Y will be the class label. Yep. So what is the learning objective? Which type of labels are you predicting? One correct label per single image. So loss function. What are our loss functions? Loss function. I want to say this is in regards to the cost function is the loss function, which is where we are getting into the chain rules and partial derivatives of what we were looking at. Unlabeled out of K, binary, it's not binary, It's not multi-label, and it's not regression. So it has to be single class. Or let's see what the actual image of a digit labels. One digit only. Cat. Okay. So yeah. So final check is image cat dog where the image can contain both would be a multi-label. But we are oh wait. Yeah. So softmax plus cross entropy no exceptions doing the bare minimum training loop. All right. So read this like a checklist, not a tutorial. What are the four irreducible components of supervised training? A model, loss, optimizer, and data. When is it possible? Okay, so let's change this to necessary pieces. Model. And what I want to do here is change things a bit from how we used to, if we think about kind of, what one second. There we go. All right. So what I would like to do personally is change things from, if I remember correctly, is I can, okay, is to change things a bit from how we were going about it text wise. I want to actually just go ahead and start drawing things out. Like I said, for me, it's a lot easier to understand what I'm doing if I can draw it out instead of writing it. So, coming back here to the four irreducible components, right? I know we've touched on these before, but now we're going to go over again with the more fundamental knowledge that we have across the entire ecosystem of AI and kind of get a finalized definition of them all. Irreducible components. Components. So you have data. We'll start with data. So we are saying that data, let's do this. So we are saying that data is the source of truth. So the data is going to be, that's annoying. So data is going to be your apple, right? Oh, 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 that is interesting. Hold on. So if I say 'image 0.png, okay. Your data set is your is this is a data set, and then a list of these would be a data loader. A parameterized function fx that maps images to logits. Kind of fuzzy on this, honestly. It's been a while. We've been stuck so long on this. We've been stuck for so long onto the mathematical aspect of everything. All right. I wish I could just. Let's see here. I see. Let's try this instead. Then here I can come here and say you have your data, which is oh never mind. Why? Yeah, that's interesting. Wonder if I can do this. Test. Realistically, I can take notes here, snip it, or clip it. Can I do this? Copy. Yes. Okay. I think I'm gonna just do that instead. Um, so we have here what is data to us, right? What does data mean to us? Well, data is going to be uh, your, let's say, apple, right? Apple. And then this is going to be, your, let's call it a zero, right? And it's going to be and label. So here you have your image and you have your label of what data is. And then next we need to look into what a model is exactly, right? So a model is just a parameterized function. X equals image tensor. Weights you don't know yet. Output logits, not probabilities. The only contract a model must satisfy, BC, height and width. This is the convolution layer, I believe, right? And your input output shape. Break one, training fails, relies. It's the last layer, size B. This should be 10, right? Images are raw pixels. Models don't see edges of cast. They see numbers, detect local patterns. Yep. Then the layers get understand more and more, combine into shapes, shape into class evidence, force compression. The model must throw information away. Each logit is unnormalized evidence for a class. Class 2 has more evidence than class 0. Okay, so these are for each class, which are the three different outputs possible. So, yes. So for one image, for this image of an apple, you're gonna, through its calculation, have come up with three different logits, which will be raw unbounded evidence for each class, right? So I'm gonna have a picture of a cornerback and receiver or a receiver. It'll come up with three different logits, be it X and Y. And then internally softmax. So you apply the softmax to those logits, to that array of logits, which helps normalize it a bit. And then you never call softmax yourself during training. Okay. Target equals 0. So softmax, I see. So the logic comes first. It's just this raw data, right? And then softmax gets applied to these logits for this one image, which then you do your loss function against the target class, which is the whether it's receiver or cornerback, and then you come to a finalized answer, which allows you to then learn the weights and biases from dealing with that cross entropy loss function, right? Ice and the layers are right. The layers are each layer here, however which way you want to go about that. And then these two output layers still being connected to every single one. Right. To which this gets connected to each one as well. Whoops. Etc. Etc. Each layer computes this, then applies a nonlinearity. That's it, repeated many times. Start with a single linear layer. In feature, out features. Weights y equals essentially as it approaches zero, or right? I want to say this is the whole as it approaches zero thing, but well, no, this is y equals mx plus b in a way. Mx plus b. Bias shift output. Without it, everything must pass through zero. All the biases from the network. Each filter slides over the image and computes. The weight times the essentially the weight. Okay, x being the input value. So the weight times that input value plus the bias. Okay. So the code first, right? So, okay. So where does the model get created from, right? Something has to create the model in the first place. Plus, how can I create my own? Not that I'm going to, but I think it's good to know exactly what the process would be to create your own model. You instantiate a class that defines a computation graph with learnable parameters. Model equals, okay, so you create the model, and that's going to create a class. At that moment, layers allocate weights and biases randomly. And then those parameters become model.parameters. So if you never call that model function, can anything train? No. So I define a subclass of neural network dot module, two required parts, your init and your forward. Define how data flows through them. Data to me is this input, and then k classes being a class is each output possible. So you call this super.init function, which is handling the parent class, and then on your initialization, uh, you are also defining the amount of classes. So receiver, cornerback, I'm just gonna have two. Uh, so you have your features, which are your convolution layer stuff. You have ReLU, which is, I want to say, the cost function, right? What is ReLU? I want to say this is a cost function or an activation function, something. What type of function is it? Or I think yeah, I guess it is activation function compared to older activations. Piecewise linear function. Okay. Yeah, it's activation function. So choosing the activation function. Okay. So we know we must create a model in order to train. So although we might not understand, so you know you need a data, you need model, and you need those two other things, which is what a data model would say loss, data model loss and optimizer. All right. So right. So let's figure out if we're just trying to reinvent the wheel here, or if this is actually how it's supposed to. Small, medium data set, standard images. Yeah. Okay. So we're going to use a pre-trained backbone and replace the final layer to output K-logits. Okay. So from my understanding, what we have written so far, uh, this is that. Or sorry, not building my own model, but using ResNet. If I'm pretty sure this right here was set up to use a certain model that we already decided on. Let's verify. Should be integers, not strings. Okay. So let's fix that up first. Should be integers. Batch size. Some quick little fixes. Okay. Add this and run. X, Y. Alright, so X, Y equals next iteration of train DO. X dot shape, X dot D type. I don't know what any of this is doing, but let's take some guesses, right? So we're going to iterate to the next set of the data loader, and we're printing out X, which is going to be the X value, right? Which to me, I guess, is saying the input. I don't know. Let's see. Breakdown is pulls one batch from the data loader. X equals images, Y equals labels. So you're saying X, Y equals next. But what I'm trying to understand, I guess, is what I guess this is Python specific iteration of training data loader. Right. And let's go ahead and let's activate that. Slide over here into our source. Let's see what happens here. So it worked as far as this goes. I got what device I'm using. I just because XY is the same as saying X, Y, right? How does it? How does train interact X, Y? Is an iterator over your dataset that pulls samples from the training dataset, groups them into batches, return batch images. Okay, I see. So it returns a batch of like, say it'll be like 0, 1, 2, but and this will be, your X's, and then this will be like 0, 0, 1 of your Y's, based off of whatever training dataset that you have. With image folder, okay. Datasets.image folder. Your dataset returns one sample like image tensor class index. The tensor class index is an integer like 0, 1, 2. Select batch size indices. Stacks the image into one tensor. Stacks the label into one tensor. So one batch is X is B 32, right? RGB 222 224 224. So if your dataset has classes B, wasp, fly, what does label 1 mean? So this is 0, this is 1, this is 2. Image folder assigns indices alphabetically. So your dataset item is going to be your tensor, the image itself, right? Which is a tensor of that. And then your label So X, Y on your data set is this. So your data loader batch is your next iteration of this, which will be what batch, and then your tensor logits equals your batch, and then the layers, right? From my understanding. Or is this, no, this is, we'll see. So logits is a class, no strings anywhere. Okay, so now we're introducing, hold on, let's do the rest of this as well. Training dot data. Let's see here. Let's just see what this does. Okay. So batch size of 5, right? Because we're working off the training data loader. So print. So first is we're here. Get comment this out too. So you're saying torch dot size 5, 3222, 3224, 224, torch dot flow 32. So x dot data type. So this is the shape of the tensor. This is the x, right? The type of x. This is the min of x. This is the max of x. And then we do y. 0 and 1, which are the labels. So if I go ahead and say folder, we do C, which is just going to be for centers, right? And that should be 0, 1. C dot png. Yeah. 1, 2. Huh. Instead of 0, 1, now it's 1, 2. Curious. Okay, that's interesting. There's something causing that. But that being said, let's first figure out what's happening here, right? So this is the output, and inside of this output, what do we have to learn here? From min to max, 0 to 1, right? From y min 0 to max equals 1. How many classes are actually present in that batch? 2. Do you have exactly 2 classes total, or did your batch just not include the other classes? Don't guess, print this. Okay, so now I'm printing training data dot classes, which is coming from this datasets dot image folder, which will have all my classes because they're set up like that. I see. So you have now your CPU receiver. So now if I say C, and then if I put C dot PNG inside of here, I run this. Now it's running that. When I add a class, only shows the last two. So there must be a way to specify the fact that you're going to have more than just two classes. That is my does one scan an instance. If you add a new after you've already created. Wait. Recreate the dataset after adding the new class folder. Nah, because okay, maybe I'm reading the output wrong. Maybe this 1, 2 is somehow including 0, right? Or something. Ah, I see. That particular batch just didn't include it. So, with that being said, if I do this to like 100, batch size of like, I guess 8 maybe. Well, how can it include that if, hold on, so, right, I want to be sure that it's possible. You see what I'm saying? I just want to make sure that, so what I'm measure whether class shows up across batches. All right, so what's happening here? Scene 0 equals 0, total equals 0 for X, Y, and trade DUI. Training data loader, total plus equals Y, nummel. All right, what is this doing exactly though? All right, we don't need this right now. So you're saying total 0, right? How many times have I seen 0 throughout going through here? Total, just in total. And then we're saying for X, Y, and training data loader, we're saying total is plus equal Y dot. What is what? Okay, okay. So you're there's num elements. Got you. And the data. Oh, okay. So the data loader, the y is going to be the output value for each input. Um, so you could imagine that these are one, two, three, four, five different inputs, and these are just the output values for those inputs. So your total number of inputs is going to be the y number of elements inside of the training data loader. From there, you say seen, how many are seen inside of the class 0, right? Scene 0 plus equals where y is equal to 0 because I'm looking for class 0 dot sum of item sum dot item. These are just your outputs to the right. Okay. Let's copy this, paste it there, delete that, rename this. Forgot I did total. Should do scene, so it's already there with the rest. Okay, so it works. It does work. It does work. It's just the fact that there was only one that messed me up in that regard. Whoops. Okay. So same thing here. Although it's just 1 and 2, it's just saying that's because it's in that batch. Right. Cool. So let's do this. Yeah, you get moments like these where things kind of get lost in translation, for lack of a better word. it's really best to just kind of move on. All right, so we understand how the training data loader is filling up its information now. It's going to have your input tensor, and then from that tensor, it's going to be an x, y of your input tensor and your output of what it thinks it should be. From there, on each iteration, each class, right? So after, okay, so using or setting up a model, right? That's what we want to do now. Set up ResNet model. Now we want to set up the ResNet model. Instantiate a pre-trained ResNet model and swap the classifier ahead. Okay, so let's come here. So we imported from Torch, from Torch import models, models. Oh, sorry, from Torch Vision, import models. We have torch.nn. So we're starting with our number of classes, because the length of training data dot classes, right? The training data is going to be based off of the image folder, which is the training dir. The training dir is this train data, which has two classes, your cornerback and receivers. So if I now say print classes, this should return 2, because we have 1 and we have 2. So yeah, so here they're just giving us feedback on what's happening. We can say print the number of classes and what the classes are exactly. The S is going to be training data. So you have your number of classes, 2, and then you have your classes of your cornerback and receiver based off of these directory folders. So from here, we are saying model, model equals models dot, which is coming from this Torch Vision models library, models dot resnet 18, which is just saying, we're setting up this resnet 18 model, which is common. Weights equals models dot resnet 18 weights dot image net 1k v1. And from my understanding, this is just going to be setting up the weights, the default weights for what's going to happen with all these layers and nodes inside of this model. But it, to me, is not going to, this is going to change, right? As it learns and everything, this will change consistently. And then model.fc equals and then dot linear model.fc.n features num classes, right? Now, what is happening with this? I don't necessarily know, but that's okay. The model equals model.toDevice, which is going to be this torch device. And then what are we're printing on model on the next parameter, model parameter device. What shape should Model X return for a batch of 5. Um, Model X. If I do model, so model itself right now is built off of this model class. So what X would be defining, I'm not really sure. Um, Possibly the weights. And if it's the weights, then to me that would be, I don't know, actually. Let's say B, because to me this is where the classes normally are, and this 5 right here would be the batch. Okay, so first, before we get into that, let's understand what we're doing with the creation of the model here. Break down the model creation from model models to model model. I always forget that the view is not the greatest. Here we are. Is that better? Okay. So model equals models.resnet weights equals the resnet weights calls a factory function that returns a PyTorch neural network module instance. The instance contains a fixed graph of layers and a final classifier ahead. Okay. So these layers to me are to find the patterns and whatnot with inside of the image. It loads learned parameters into every layer. If you pass none, they're randomly initialized. Model whose forward pass maps an image tensor by default. Okay, I see. So the by default you have 1,000 classes. Um, Model FC. So this line here, you're saying ResNet ends with a layer called fully connected. You replace it with a new linear layer that outputs num class logits. So two logits, right? Your data set is not ImageNet. You need logit size to your class count. New layers, weights, and biases. The new layer to this final layer, this fully connected layer. Okay, so we have a FC layer when you create a model, and then you're creating a new, essentially a new layer here, which you're inputting your the input features to that final layer, um, and you're setting the output of the classes to the num classes, which are coming from my trading data classes, which comes from the image folder, allocating 0 and 1 to the different classes inside of the trading data directory. Whew, okay. What happens to weights? The weights are randomly initialized. and then moves all parameters and buffers to the target devices. If device is CUDA, putting the model on GPU memory, it's CPU though, so implied but critical moving inputs you must do x equals x to the device, y forward loss will crash. Okay. So print next model dot parameters dot device. Let's take a look at what that does. CPU. And this is us getting information for that ResNet 18 model. Wonderful. So now we are checking the output shape equals model X. No, because first you have to do this, right? First you have to say X equals X dot to device, and then Y equals Y dot to device. But where are X and Y coming from in the first place? Ah, it's here. So you're saying X, Y equals next iteration of my training data loader. And then we send X to the device, Y to the device, and then we're saying logits equals the model, running this model with the input of X being whatever first layer, um, whatever first image of the batch of the data loader batch that they have, right? Then we want to print out my logits.shape to see what that output is like. Okay. So I don't think that necessarily does, because it's saying batch 5 with two different classes. Build the training pieces, loss plus and do one train step. All right, so let's, I'm curious to just do this and see if this just works, right? Data loader, print. I'm curious to see if this just works, and then if we can go ahead and reverse engineer it from there. So I get a loss amount. Cool. So this is us definitely getting into the more programmatic side of things. Like I said, getting a number now for our amount of loss. Is it randomized every time, or am I? It is a different image. Okay, so each time it is also a different image, which is triggering a different amount of loss. I I am kind of hand waving a lot right now, like oh yeah, it just kind of does it and then it works and yada yada. But I think we have a stronger understanding about kind of what's happening here than we're giving ourselves credit for at the same time. So I would say stopping here is good. We have actual code in place, actual things being ran and done that will allow us now to kind of come back tomorrow and reverse engineer a bit of this down here and get to a more full all around understanding of just what's happening, right? But especially with the optimizer, understanding what this loss dot backwards is doing. But to actually be able to get output based off our training data is the first step, realistically, right? Um, and from here, all we can do is just keep getting better and better, and keep understanding one thing at a time. So had a great time. Knocked out our hour. And I will be back. Honestly, what I might start doing is having multi-day streams. So, do an hour, take a break, do another hour to keep the same progress and process of, just 1 hour at a time. Uh, you get to my 500th video and it's like, okay, if I spend 500 hours on AI engineering, I'll get to this level, right? But I think besides that, that'll allow me to kind of keep moving forward at the pace that I'm looking towards while still being realistic for others, right? Still just putting it in a position of, if you want to follow an hour a day every day, this is how. If you're looking to expedite it, then just watch multiple videos, right? But definitely keeping it around that hour length for each video is key. So that's the future plan. Hope you guys learned something today, and I will see you in the next go around, man.